15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the podcast known as Space Nuts, where we talk astronomy and stuff. And my name's Andrew Dunkley, and joining me from the Australian Astronomical Observatory is Fred Watson. Hello, Fred.
Hey, good day, Andrew. How are you going?
I'm quite well, thank you. And you?
I'm very well, thanks. I'm just fiddling with my levels here to make sure that we are, we're talking on the same wavelength, and none of us is bellowing at the other one. So, yes, all good, thank you. Take it away, Andrew.
Thank you, sir. Now, today we've got a few things to talk about. An exoplanet with a very strange but interesting atmospheric condition, and an Australian rocket that has been created in a very different way, and it works. Yeah. And we've got a couple of listener questions. One about pregnancy in space, which we alluded to a week or two ago. And the question of flat Earth believers. Why do they believe it, and why are they wrong? We'll have a look at that soon. But first, Fred, this exoplanet that has been discovered with this unusual atmospheric trait. What's this all about?
Yeah, so it's a great story. So the headline in the news release, which comes from the European Southern Observatory, is "Inferno World with Titanium Skies." Doesn't that paint a picture?
It sounds interesting.
Yeah. So what's happened is, and this is really, really clever astronomy, there is an exoplanet. So this is a planet going around another star. It's got the wonderful name of WASP-19b. It was discovered by a project called WASP, which are, they look for exoplanets. They look for the signature of a planet passing in front of its parent star. What happens is the parent star's light dims as the planet goes in front of it. So that was discovered quite some time ago. We know this planet is what's called a hot Jupiter. That means it's of the order of the size of Jupiter, extremely hot because it's so close to its parent star that it orbits in, guess what? Not a year, 19 hours.
Wow.
So 19 hours is 1 year for this planet. And the estimate is that its atmospheric temperature is about 2,000 degrees Celsius. Now, that clearly is too hot for life as we know it. It's probably too hot for life of any kind. But it is a temperature that's kind of at the lower end of the scale of temperatures for stars. So this is not a star. It's definitely a planet, but has some characteristics of a star.
It's a
stanet.
That's about as far as it gets.
Yes, or it could be a stanet. Yeah, I don't know. We need to invent a name for those. Planetar or something like that. Anyway, it's a big planet, not quite a small star. But what that means,
I've got a name. A staroid.
Oh, I like that.
You like
it?
That?
It sounds like something you'd buy in a chemist shop.
Yeah, it does, doesn't it?
Can I have a box of steroids, please? No, we won't go there. Anyway, the thing about this planet is that it may be expected that its atmosphere has some similar sort of chemistry to certain stars. And what has now happened is that the scientists at the European Southern Observatory, which you'll remember operates the 4 giant dishes of the very large telescope down at Paranal in Chile, they have used one of their instruments to very, very cleverly analyze what chemicals are present in the atmosphere of this planet. And the way they do that is that as the planet passes in front of the star, some of the light's blocked out, and that's why the star's light dims. But some of the light actually passes through the atmosphere of the planet. You can imagine this thing, the disk of the planet passes in front of the star. There's a little band around it, a kind of annulus, in which the light can pass through the atmosphere. I'm making all the gestures here, which I know you can see, but
I can see.
Nobody else.
I'm relaying them telepathically.
Thank you, telepathically. That's good. And so when you do that, it means that if you apply a spectrograph to the light of the star, which is really all you can see, at the time when the planet passes in front of it, and a spectrograph, of course, breaks the light into its rainbow spectrum of colors and reveals this barcode of information that tells you what's in there. When the planet passes in front of the star, that spectrum is going to change. You will get features in it, in the barcode, which belong to the planet's atmosphere rather than the star itself. Are you with me so far?
I am, sort of. Yes.
Yes. So the light going through the planet's atmosphere picks up a signature of what's going on in the planet's atmosphere, and we can decode that with the spectrograph. And what they have found is what we call bands. Actually, bands are a particular type of barcode. It's nothing to do with music. It's just lots and lots of different, very fine spectrum lines. That's the technical term. Mm-hmm. And those bands are due to titanium oxide, a compound in the atmosphere of the star. It's cool enough for these molecules to form. If it was much hotter than that, they would dissociate into titanium and oxygen. But titanium oxide is interesting because it's found commonly in the atmospheres of cool stars. In a way, that the highlight of this story is that they've done it at all. It's an extraordinary achievement. But it is the first time we have found titanium oxide in an exoplanet atmosphere. It's a kind of, a step forward. It doesn't mean that if you stood on the surface of the planet, heaven forbid, because at 2,000 degrees Celsius, you wouldn't last long. It doesn't mean that you could look up and see these, steely grey skies of titanium. It just means that we know that this compound, titanium oxide, is present in the atmosphere.
On the plus side, though, your McDonald's hamburger and chips would be hot.
They'd certainly be hot, and they'd probably be shiny as well with the titanium. Yeah, so a great story and a great achievement from the scientists at ESO.
Quite amazing. And what I find fascinating is that the more we discover, the more things seem to be different or beyond what we think is normal. We're starting to find all these unusual traits about exoplanets and other stars and black holes and you name it. The better we get at searching and finding, the more variation we find, I suppose.
That's right. The more extraordinary things we discover, that's the bottom line. It is amazing. There is an implication of this titanium oxide. If there's enough of it, apparently it acts as a heat absorber. And so it may, stop heat leaving the atmosphere. And the suggestion is that might give you what we call a thermal inversion, which we see commonly on Earth. The thermal inversion means the temperature is higher the higher you go in the atmosphere rather than the other way around. Normally the temperature, as we all know when we climb on board a jet and see the temperature outside dropping to -50 or something, that's because we're a long way from the surface of the Earth. If you're a long way from the surface of this planet, it might be getting even hotter if there is a temperature inversion due to the titanium oxide.
Quite incredible. All right. Who knows what else we're going to find out there, Fred, but I'm sure we'll find something soon.
And I'm sure that you and I will be talking about it when we do.
Indeed. You're listening to Space Nuts. My name's Andrew Dunkley, and I'm with Fred Watson.
Okay, we checked all 4 systems, and keying with a go.
Space Nuts.
Now, Fred, we're going to talk about a rocket. Now, as rockets go, most people are very much aware of them, particularly those of North Korea. But the rockets that people think of stand on platforms. They're stories and stories high, and they blast people and equipment into space for all sorts of reasons, or they take satellites up or whatever. This is not one of those. This is a different rocket, and it was an Australian creation. Now, historically, we haven't had much of a rocket history except for way out west in a place called Woomera, actually way down south. As far as getting into the rocket industry is concerned, it's not been front of mind until now.
Till now, indeed. That's right, Andrew. There is actually some quite extraordinary technology being developed in Australia. Just to give you a bit of background there, the research group at the University of Queensland that works on hypersonics, these are essentially rocket engines, but they're air breathing and they work at very high speeds and very high altitudes. They're apparently doing world-leading work. And there is a hypersonics group also at Sydney University. I was talking to one of their PhD students a couple of days ago. Great guy and a great project.
This is what happens. They do this stuff, but they forget to tell people.
They don't tell people, yeah.
So that's different from scramjet technology, because that sounded much the same.
It is related to that. That's right. It's a scramjet, supersonic combustion ramjet. So ramjets are. Actually, I tried to build a ramjet when I was about 12, but I didn't realise you had to get it to the speed of sound before it would work. So
I actually built a jet engine with a mate of mine in a garage once. We used aluminium cans and cut the fins and put them in a tube, and we made one very catastrophic error. We gravity fed fuel into it.
Yeah.
I'm sure you know what happened.
Yeah, that's right. So it did what mine did too, just burst into flames.
Exactly.
Basically.
It did move, though, very quickly.
That's pretty impressive. Mine didn't. Well, never mind. That's completely off the story. And it's totally, the hypersonic stuff is exciting, but it's not what we're talking about today. So anybody listening to this, and somebody must be listening, you can forget all that, because what I'm going to talk about now is some work being done in Melbourne actually, I think it's Monash, yes, Monash University. And it's basically in response to an arrangement with a private company, a university-affiliated company. And the idea is that with 3D printing, you can do all kinds of new things. Not only printing paperweights and things like that, but you can make rocket engines as well. And this department at Monash University have the reason why we're talking about this story is that they have just successfully tested their first 3D printed rocket motor. And it works, actually, from what I've seen, it works staggeringly well. 3D printing, of course, is it's got a fancy name. It's called additive manufacture, rather than most other manufacture, which is subtractive manufacture, where you machine things and get rid of the bits of metal you don't need.
Yeah.
Like car engines are made that way.
This is basically the opposite.
It is exactly the opposite. You simply add the material that you do need, and it means you can create shapes which are impossible to shape by normal methods. And so the bottom line in this story is that the department in the University of Monash has fabricated this rocket motor. They've tested it. It works. It will probably be developed further to be used actually in flying rockets when we in Australia get our space agency eventually. But there is a special feature of it, Andrew. And I thought I knew my rocket engines, but I didn't know about this. There is a design which differs from the normal rocket motor. You remember, when you think about the engines on the back end of the space shuttle or something, it's a very prominent bell-shaped machine.
Yeah, and the Saturn V's had those as well.
Absolutely, yeah.
Amazing.
That's the conventional shape of a rocket motor. Most of the space work that's done in the world uses engines that are shaped like that. The bell shape sort of confines the what's basically an explosion. It confines the combustion of the gases to basically provide the thrust. It points it all out the back, and the rocket goes the other way. But there is another type of rocket motor which is called an aerospike, and the name kind of gives it away because in the middle of it there's a spike. And what you do is you burn the fuel along this spike, and the atmospheric pressure confines the outer edge of the burning flame. The spike gives it some direction, but it eliminates the need for this bell. And there are certain advantages to an aerospike because as you go up through the atmosphere in a rocket launch and the pressure drops, the aerospike automatically compensates for the pressure drop, and basically the thrust stays the way that you want it. So you've got a more constant thrust as the rocket goes up through the atmosphere. So fantastic stuff. Sorry.
Would that make it more fuel efficient?
Exactly. That's right. Fuel efficient and combustion efficient as well. The Kiwis are launching rockets, as you and I have spoken about.
Yes.
They've now got a rocket range on the eastern side of the North Island, And they too fly rockets with 3D printed engines, but I'm not sure whether they are aerospike engines or whether that is something new for Australia. I should check up on that and find out.
Yeah, they've published pictures and a story and a small video of the rocket engine being ignited, and it really does seem to have some pretty darn good thrust. It
Great
pumps
stuff,
out a
isn't it?
flame, doesn't it?
Yeah, it's great stuff.
Yeah, you could weld with that thing.
Oh, you could. If you could hang on to whatever it was you were welding.
Yeah, very impressive and not surprising. Monash University is probably one of the top unis in Australia and well respected and named after one of my great heroes, John Monash, who was a World War One general with the Australian Imperial Force in World War One. Fascinating man. I've read 2 of his biographies and just a remarkable individual at a very, very difficult time in world history. But worth a check out if you want to look at the Aerospike, the Monash University rocket. We're on our way, Fred. We're going to be up there soon. Yay.
I hope we are. Yeah, absolutely.
No more hitchhiking with NASA.
No, that's right. Yeah.
You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we're going to try and deal with a couple of audience questions. We love your questions, so keep them coming. You can send them to us on Facebook and Twitter. We're going to try and tackle 2 today. One from John Bassick, who asked us a question which we alluded to a week or 2 back about pregnancy in space. And John wants to know if a female astronaut was on a space station for an extended time, got pregnant, which would be very naughty, and stayed in space with no gravity for the term of her pregnancy and gave birth on the station, would there be any effect on the baby, and can the baby come back to Earth? Being that there is gravity, how would it affect the infant is basically the question. Very good question, and one worth investigating.
Absolutely, and as we said the other day, this was something that we needed to check out. The bottom line is, well, yes, you could make babies in space, and you could have pregnancies in space, but the academic opinion, the academic view of this, seems to be that it might not be a good idea, and the reason is all about the known effects of microgravity on, the development of fetuses in other animals than humans. So there have been experiments done on, wait for this list, geckos, sea urchins, rats, even birds. And the bottom line is that, the viability of the fetus is lower. So they tend not to survive. And occasionally there are strange abnormalities that crop up. On top of that, a space pregnancy might be quite a taxing experience for the mother. And it's one that has been looked at in quite some detail, a question that's done that, because there are all kinds of potential issues. What about if we ever were colonizing Mars or something like that? It's really something that needs to be thought through about how the lower gravity on Mars might affect pregnancy and fetal development.
Yeah, Kim Stanley Robinson wrote a very interesting series of novels about humans colonizing Mars, and one of the things he actually alluded to, and you and I have spoken about him before because his research was amazing. So what he writes could actually be some form of reality if we ever did it. But one of the things he writes about is that people who ultimately were born on Mars grew to be quite tall because it's lower G. And so they were tall, slender people, much taller than we would think is normal. Yes. And I would imagine a zero-G pregnancy would cause some sort of changes in the physiology of the child. And one of the things that they seem to have a problem with in zero-G environments is muscle wastage and bone density issues. So if a baby was born under that environment, I would wonder about whether or not they could actually be normal.
Yes, exactly. That's right. And it's because of all those doubts, Andrew, that NASA has a policy that does not allow pregnancy in space. And something I didn't know, but any female astronauts flying to the space station are regularly tested during the time before they make their flight. There's sort of ethical issues as well about whether people get together in orbit. So far as we know, that has never happened. I think there's been plenty of speculation about it, but it's not anything that's ever happened. And it's partly because, on the space station, your mind is focused pretty well on different things. But the ethical issues are really something that have been considered, and so the whole idea is totally frowned upon.
So basically the answer to the question is we think it could cause problems. We don't know exactly what might manifest itself in the process, but not recommended, basically.
Not recommended, that's right. That's the answer.
Okay. Thank you for your question, John. I hope we answered it adequately. Now we've got a question from Jonah in Portland. He says, "Hi guys, love the show. I have a serious question for Dr. Watson." Anyway, my brother is a flat Earth believer, unfortunately. Flat Earth believer. We recently got into an argument over it. What can I tell him that can undeniably prove that we actually live on a round planet? Actually, Jonah, I'll preempt Fred here and tell you it's a sphere. I know this is ridiculous, but these are the times we are living in. Again, I love the show and hope you can help me out. We'll do our best, Jonah.
So actually...
he wasn't born in space, he was born in a whale. But let's carry on.
Oh, come on. Jonah, forgive my colleague for not only insulting you with the whale joke, but insulting me by doubting my PhD. And just to prove that I've got a PhD, actually the Earth is not a sphere; it is an oblate spheroid.
I know. I was just sort of making it simple for
never mind. That's all right. So it's spherical. So, but it's a great question. It really forces you to think about these things. So when you go back to really ancient times, before the Greeks and the Romans, people knew that the Earth was definitely curved in some way, because if you imagine yourself in the Middle East or somewhere, you trek southwards or northwards or whatever, and what you see is that you see different constellations in the sky. You start to see, as you move further south, you would eventually, if you got far enough south, you'd see the Southern Cross and things of that sort, which are not visible from further north. That doesn't tell you that the Earth is a sphere, but it does tell you it's not flat. In fact, the Earth could be cylindrical if it was like that, because you're going over the curvature. But the clincher, and this is how the ancient Greeks knew that the Earth was spherical, is that when the Earth casts its shadow on the moon in an eclipse, that shadow is always circular, and it's always the same size. And so if you think about it, if we were on a flat Earth, which had a boundary somewhere, an eclipse can take place with the moon anywhere in the sky. So if the eclipse was while the Earth was while the moon was low in the sky, you'd see a kind of flat shape.
Yeah, good point.
Rather than seeing the curve that we see.
Yeah.
So it's the curve of the shadow of the Earth that told ancient people that the Earth is spherical. So they knew that from way beyond the birth of Christ.
How clever.
Of course, we know it because most of us have got in jets and basically flown around the Earth to a place where...
The other thing that would prove it is orbit, because orbiting the Earth is basically a falling motion. You're just constantly falling, and you can only do that if you're going around something.
Yes, exactly. So you couldn't go into orbit. That's quite right. So it's fairly well sewn up. I actually had an email from a flat Earth person. It was probably a year or so ago, maybe 2 years ago, which I answered with the same sort of patience as we've just answered that. Time to go, Andrew. We've got to get off this flat Earth.
And well, the other thing that proves it is the water's still here. I mean, if it was all running off, we wouldn't have any left.
There's probably a dam somewhere.
That's what it is. There's just a big wall around it. There you go, Jonah. Tell that to your brother, and I bet he won't believe you. But anyway, we tried. We tried, Fred.
Yeah, we did. That's right.
All right. Keep your questions coming. We love to answer them because it saves us research. Although that one didn't. No, the one before didn't. Anyway, thank you, Fred. As always, great to talk to you.
You too, Andrew. Good to have a chat again, and I look forward to the next one.
Fred Watson from the Australian Astronomical Observatory, and from me, Andrew Dunkley. Thanks for listening. You can catch us on your favourite podcast platform. Don't forget to listen to Stuart Gary as well with Space Time. He does his report in a more news-style format, but still very much worth listening to. And we will catch you next time on the podcast known as Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.